As far as business calculus is concerned, this is one of the most important sections we'll do all semester. It concerns a topic in calculus known as optimization. Optimization is the process of finding the maximum or minimum values of a function. In business, you would want to find the maximum profit while having a minimum cost or a minimum average cost. And we extend that to some other ideas as well. But that is our focus today. Inside this section, we'll be looking at the Extreme Value Theorem, and we'll find absolute extremes from real-world situations. We'll apply those principles to business and economic situations. And then we'll also look at a topic called the elasticity of demand to determine how price and demand changes with respect to each other. So let's go ahead and get our definition of absolute extrema, and this is absolute maxima and absolute minima. So suppose we have a function f, then we say that f of c is the absolute maximum if f of c is greater than f of x for all the x's in the domain of f. So in other words, this f of c is the largest y value that the function takes on over its entire domain. So this is a little bit different than relative maxima. You could have relative maxima here and there and everywhere else, but you can only have one absolute maximum value. It's that one y value that is the largest for all values. And of course, it doesn't have to exist, but if it does, then that value is unique. Now, by saying it's unique doesn't mean that it can't happen in multiple spots. You can take on the absolute maximum value at different numbers along the domain, but it's still that one largest y value. On a similar note, if f of, suppose we have f of c, and that is called the absolute minimum of f of x if this f of c is the smallest y value. So f of c is less than or equal to f of x for all x in the domain of f. So that's the smallest one. Let's look at this concept graphically first. Example number 1, find the absolute extrema for each function graphed below. So on the function here on the left, we can see it's sort of a short function here. It's got a finite domain, or bounded domain, let me say. And so what we're looking for is the lowest y value and the highest y value. Well, the lowest y value occurs at this point right here. So we would say that the absolute minimum value is -1. It's the y value right here at this point, right here. Let me rewrite that. -1. And then what is the largest y value? Well, that occurs right here, and that's at 3. So what we can say is that the absolute minimum value is -1, and we'll put in parentheses here, that it occurs at x equal -1 as well. And the absolute maximum is equal to 3, and that occurs at x equals 4. So in this problem, we had both an absolute min and an absolute max. On the function in the middle, let's look for the absolute minimum. Well, we don't have an absolute minimum. You can see right here that the arrow indicates that it goes down forever. So for absolute minimum, there is none. There is no smallest y value. Now what about absolute max? Well, the absolute maximum is right here, and that would be a value of 4. It's the y value. And we'll say that this occurs at x equals 2. And for a third graph, we see that it goes down forever and it goes up forever. And so therefore, for both of these, absolute minimum, there is none. Absolute maximum, there is none as well. One of the most important theorems of this section is called the Extreme Value Theorem. It says a function f of x that is continuous on a closed interval, a to b, obtains its absolute extrema, so both a min and a max, on the interval at either a critical number inside the open interval from a to b or at an endpoint of the interval from a to b. So if you have a continuous function, so there's two conditions here, continuous function and a closed interval. If you have that, then you do know that it obtains both extrema on the interval at either a critical number or an endpoint. Let's reconcile that with the pictures above. In, let's call this number 1, picture 1, notice that we do have a closed interval because it starts at this point and it ends at this point. So that's the A and the B. And we did obtain both an absolute minimum and an absolute maximum. It happened that these were both at critical numbers because you can see that at these numbers, there is a horizontal tangent line, which is where the derivative would be equal to 0. Now, it could be at the critical numbers, or it could have been at one of the endpoints. In this case, it was two critical numbers. If we look at number 2 and number 3, the extreme value theorem does not apply because the intervals for the domain are open. They go on from negative infinity to infinity for both of those. So we can gain nothing from the extreme value theorem for those two. Example number 2. Find the absolute extrema of f of x is equal to x cubed minus 6x squared minus 15x plus 5 on the closed interval -2 to 8. So the extreme value theorem applies. And so we find the derivative. The derivative is 3x squared minus 12x minus 15. And we want to find the critical values, so we set it equal to 0 and solve for x. Factoring out of 3, I get x squared minus 4x minus 5 equals 0. Factor. We get x minus 5 and x plus 1. Which gives me x equals 5 and x equals -1. No solution from the 3 over here. And now to determine which is the absolute maximum and the absolute minimum, we test the endpoints and the critical values in the original function. So we're just looking for whichever one is the biggest and whichever one is the smallest. So the endpoint here of -2, that's the left endpoint. And I've already done these. I'm plugging these into the original function to determine which one is the largest. So -2 was 3. Plugging in this critical value of -1, I get 13. Plugging in the other critical value of 5, I get -95. And then the last endpoint, f of 8, is also 13. And then whichever one is the largest and whichever one is the smallest, those are our winners. Now for the largest one, we have a tie, which is fine. the absolute maximum value is unique. That value is 13. It happens to occur at two different places, but that's okay. It's still the largest y value. And negative 95 is the absolute minimum value. And we're guaranteed by the extreme value theorem that there are no values of this function on this interval that are larger or smaller than 13 and negative 95. Now let's look at example 3. And example 3 is almost the same, but notice that it has a different domain. This time it goes from negative 2 to 3. So when we take the first derivative and set it equal to 0, we still get x is equal to 5 and x is equal to negative 1. But this time, notice that x equals 5 is no longer in the domain that we are looking at. It has been excluded because the domain only goes up to 3. So we can only test the 3 numbers that we have here. We still have negative 2 as an endpoint. We still have negative 1 as a critical value inside this domain. But now we have to cut it short, and the right endpoint is 3. F of 3 is negative 67. And so we have an absolute maximum of 13 and an absolute minimum of negative 67. Example number 4. Find the absolute extrema of f of x is equal to x squared plus 2 over x for x greater than 0. So first observation is that the extreme value theorem does not apply because this is an open interval. This is 0 to infinity, so that's open. And so the extreme value theorem does not apply. So we'll have to do this one the old-fashioned way. So take a derivative, and the derivative of x squared is 2x. The derivative of 2 over x is negative 2 over x squared. And if you haven't figured this one out yet, let me show you real quick. If you have 1 over x, that's equal to x to the negative 1. And so now if we take the derivative, that would be negative 1 times x to the negative 2, which is equal to negative 1 over x squared. And then you can replace this 1 with whatever number that you want. So in this case, it was a 2. And it's a little trick. It comes up often enough that I've memorized this one as a rule. So you might benefit from doing that as well. All right, let's find some critical values. We're going to set this equal to 0. And the first thing I think I will do is I will multiply both sides by x squared to get rid of the x squared in the denominator. So let me rewrite my equation. And then I'll come in here and multiply this by x squared and x squared. That gives me 2x cubed minus 2 equals 0, because this x squared is going to distribute to both terms. Now to solve this, I move the 2 over. I get 2x cubed equals 2. Divide by 2, and I get x cubed is equal to 1. And take the cube root of both sides, and the cube root of 1 is 1. Now we want to look at the sign chart, but we have to be careful. We know that the interval is an open interval that starts at 0, but it does not include 0. So instead of having the full line for the number line, it's a ray with an open circle at 0. Now, why do I need to acknowledge that? Why can't I just use a regular line? Well, it has to do with where you pick up the testing points. Because the function that we're dealing with has a limited domain, you're not allowed to pick testing points that are outside that domain, in addition to having to solve satisfy rather the positioning based on the partition numbers. So I can't pick 1, I can't pick 0, I've got to pick numbers in between 0 and 1, and then 1 to infinity. I couldn't pick -4, for example, because -4 is not in the domain of this function. 1 was a 0 of the derivative, so we have that. And then I'm going to test the derivative at 2. So this would be 2 times 2 minus 2 over 2 squared. That would be 4 minus 1/2, which is 3.5, which is positive. So these are all positive. And the multiplicity of the 1 was odd. So that means it's all switching sides here, so it's negative on that side. Well, that's perfect. That's exactly what we're looking for. We know that the function is, the regular function f is decreasing followed by increasing once it hits 1. So that's going to be a minimum. But notice the behavior of the function. From 0 to 1, it's decreasing, and 1 to infinity, it's increasing. And that's it. There's no other funny business. There's no other vertical asymptotes to allow the function to sort of do anything else. This is it. So this function sort of has two behaviors. It's not a parabola, but it does look something like this. And that's it. And so because it's only doing sort of two different behaviors, it's decreasing followed by increasing, this minimum is not only a relative minimum, but it's an absolute minimum, because there's no other opportunity for the function values to get lower than whatever this y value is. And so that's sort of a unique situation. Now we have to have a couple of criteria to let us do that. So let's write that down. And those are the following. F has to be continuous, CTS, on the interval for the domain. And because of that, F has an absolute minimum at x equals 1. And F has no absolute maximum. Now we still need to figure out what the absolute minimum value is, so we'll plug in 1 into the original function. So that's 1 squared plus 2 over 1, which is 3. So the absolute minimum value is 3, and there is no absolute maximum value. So I think that's kind of neat just in and of itself. This function, x squared plus 2 over x, the smallest value that could ever be is 3. There's no way for it to be 1 or 2 or anything lower than 3. The second derivative test for absolute extrema is a little more powerful than the previous second derivative test that we already knew. Let's take a look at it. If f of x is continuous on its domain and x equals c is the only critical number with f prime of c equal to 0, then the following two conditions can apply. If the second derivative is positive, greater than 0, then the absolute minimum of the function f is f of c. And if the second derivative is negative at x equals c, then the absolute maximum of f of x is f of c. So recall what we had previously, right? We had a second derivative test that just worked on any critical number. And what that said was if you had a value of x and you did a second derivative and determined that that value was positive, then that represented the fact that you had a concave up section of the graph. And so this was going to be a relative minimum. And if you had a section of the graph that was had a second derivative that was negative, then that graph was concave down, and then this point was a relative maximum. So what's changed is the fact that we only have one critical value at x equals c. So we have uniqueness of the critical value, and that upgrades its status from being a relative min or relative max to being an absolute min and an absolute max. And that's the difference. So if you only have one critical value and you use the second derivative test, then that produces an absolute min or an absolute max. Example 5 says, use the second derivative test for absolute extrema to find the absolute maximum of this function f of x is equal to x minus 1 over x squared. So first, let's find our critical values. We'll use the quotient rule. So the derivative is 1 times x squared minus 2x times x minus 1 over x to the fourth. Let's simplify. So we get x squared minus 2x squared plus 2x divided by x to the fourth. And let's simplify the top. I'll put the 2x in front to make it look nice. X squared minus 2x squared is x squared over x to the fourth. And finally, I can factor out an x. That leaves me with 2 minus x over x to the fourth. And we get some cancellation. We get 2 minus x over x cubed. So that's our derivative. Next, we need to find the critical values. And so let's find where f prime is equal to 0. We do that by setting the numerator equal to 0 and solving for x. We get x equals 2. And then we should set the derivative, or at least find where the derivative is undefined by setting the denominator equal to 0. And that would be x equals 0. Now this is not a critical value because the original function had x squared in the denominator. So x was not allowed to be equal to 0 for the domain. Since it's not, since 0 is not in the domain of the original function, it cannot be a critical value down here. So we're good there. All right, now what are we looking for? We're looking for the absolute maximum. We're supposed to use the second derivative test. Because we're supposed to use the second derivative test, we need to take the second derivative. So let me rewrite the first derivative. That was 2 minus x over x cubed. And now the second derivative would be the derivative of the top times the bottom unchanged minus the derivative of the bottom times the top unchanged divided by the bottom squared. That's negative 1 times x cubed minus 3x squared times 2 minus x divided by x to the sixth. Let's simplify. So we get negative x cubed minus 6x squared plus 3x cubed over x to the sixth. That is equal to 2x cubed minus 6x squared over x to the sixth. Factor out 2 and x squared, and that leaves me with x minus 3 over x to the sixth, and that would be 2 times x minus 3 over x to the fourth. Now I don't need to set this equal to 0 and solve. I'm not really finding concavity. All I'm going to do is test the critical value inside this second derivative. So now we test. So f double prime of 2 is equal to 2 times 2 minus 3 over 2 to the 4th. So that would be 2 times negative 1 over 16, which is positive times a negative times a positive, which is negative. So the second derivative is negative at the critical value of x equals 2. That implies that the function there is concave down. And if the function is concave down, then that means at negative 2, we have an absolute max. Now it's an absolute max because of the second derivative test for absolute extrema, because x equals 2 is the only critical value, thus producing an absolute max. At x equals 2. Let's figure out what that absolute maximum value is. I'm going to do f of 2, which would be 2 minus 1 over 2 squared, which is 1/4. So the maximum value of this function is 1/4. We have a business example in example number 6. A company determines that the price demand for selling X thousand boxes of chalk is P of X equals 3 minus 0.01 X, and the cost for producing X thousand boxes of chalk is C of X equals 0.02 X squared plus 1.5 X plus 12 thousands of dollars. Question A. How many boxes of chalk should be produced to maximize profit? So we need to come up with the profit function. Recall that profit is equal to revenue minus cost. And also recall that revenue is equal to X times P of X, the number of units times the price per unit. So let me start with the revenue function. That's X times P of X. So that would be X times 3 minus 0.01 X. And that's equal to 3x minus 0.01 x squared. Then we're going to have the profit function, and that's the revenue function minus the cost function. And the revenue function was 3x minus 0.01 x squared, minus the cost function, 0.02 x squared plus 1.5 x plus 12. And then we need to simplify that, and that's equal to negative 0.03 x squared plus 1.5 x minus 12. Don't forget to distribute the negative to these terms here and add to the other terms. Now we are looking for how many boxes should be produced to maximize profit. To find the maximum, we need to find the derivative. So we'll take the derivative here. That's negative 0.06x plus 1.5. Set that equal to 0. And solve for x. So we get negative 0.06x equals negative 1.5. Divide by negative 0.06 and you get x is equal to 25. Now be careful at this point. All that we have shown here is that 25 is a critical value. We still need to demonstrate that this is where the maximum occurs. It's a single critical value. So I'm going to use the second derivative test. The second derivative of the profit function, I'm going to start with the first derivative, and I'm going to take its derivative, and its derivative is really just 0.06. There are no x's left in this function, which means this function is always concave down. Since it's always concave down, that means no matter what I put in for the critical value here, 25, it's always going to be negative. It's always negative 0.06. So that does demonstrate that it is an absolute maximum by the second derivative test for absolute extrema. All right, now let's convert that into a meaningful answer. X equals 25. Recall that X was written to represent thousands of boxes of chalk. So that means the number of boxes should be 25,000 boxes of chalk. And that's how many boxes should maximize the profit. Question B is, what is that maximum profit? So to find the maximum profit, you take 25, this is the X value representation of the 25,000 boxes of chalk, and you plug it into the profit function. When you plug that in, you get $6,750 in profit. Question C says, how many boxes of chalk should be produced to minimize the average cost? So I'm going to create a new function called AC for average cost. That's just the cost function divided by X. You're taking the total cost for producing X thousand boxes of chalk, and you're dividing it by that X itself. So this is going to be equal to 0.02 X squared plus 1.5x plus 12 divided by x. And I'm going to go ahead and divide this into each of the terms here. So this would be 0.02x plus 1.5 plus 12 over x. Essentially, you're just splitting the fraction up into the three parts that it came from. Now, one quick side note on this formulation. Is this formula actually giving me the average cost per unit? And the answer in this case is yes, because the C of X is giving me thousands of dollars in total cost, and the X is giving me thousands of units. So in this case, this is sort of crude, but that's basically what's happening. The thousands are canceling, and this is giving me dollars per unit. So it is an actual average cost per unit. And so you do have to worry about that a little bit, but just make sure that you are getting dollars per unit, and if not, you can alter that by dividing or multiplying by a specific number. All right, let's continue on now with the rest of the problem. So we want to find the average minimum average cost. So we take a derivative, and the derivative is 0.02 minus 12 over x squared. Now you see why I opted to split this up. I didn't need the quotient rule. I just took a regular derivative, and I'm using that new trick that I taught you, and it sort of simplifies things pretty rapidly here. All right, we set this equal to 0. Let's solve for x. Move the 12 over x squared to the other side. Cross multiply by the x squared. And we get x squared is equal to 600. And x is equal to 24.495. Now, does this actually produce a minimum? Well, to figure that out, let's use the second derivative test. I'm going to take the second derivative of the AC function, and the second derivative is positive 24 over x cubed. Basically, you're just taking the derivative of this part because that one is 0. And now if I plug in 24.495. I get a positive number divided by a positive number, which is positive, which means that the function is concave up, producing a minimum. And since this was the only critical value, it's an absolute minimum. So the answer to question C was how many boxes of chalk should be produced to minimize the average cost. The answer is 24,495 boxes of chalk. And then question D was, what is the minimum average cost? So AC at 24.495 is approximately $2,480. Finally, we look at elasticity of demand. Elasticity of demand measures how responsive or sensitive demand is to the changes in price. And so the definition of elasticity of demand is here in the box. It says if Q is equal to D of P units of a quantity are demanded by the market at a unit price of P. So Q is going to be the number of units demanded. D is a demand function, and that's going to tell me how many units are demanded, but the of P part means that it's based on price. So that's just a little translation there for you. Let's pick it up. Where D is a differentiable function, then the price elasticity of demand of the commodity is given by this function. Now I'll give you this function on a test, and so that you will have that. You do not need to memorize this, but it is E of P, so E is elasticity. E of P is equal to negative P over Q times dQ dP. So that's the derivative of the Q function based on P. So that's the derivative of this function over here. And this represents the percentage rate of decrease in demand Q produced by a 1% increase in the price. So remember that price and demand are inversely related, right? Like this. So as the price goes up, the demand falls from this position, say, down to this position right here. Now, the 1%, that comes from the derivation of the function. You can read about that derivation in the textbook if you'd like. I'm more interested in you being able to use this and to construct the meaning behind what the elasticity is. Example 7. Suppose the demand Q for a commodity is given by Q is equal to 200 minus 5P. So this function right here is the D of P demand function. This has a limited domain from 0 to 40. And the question is, find the elasticity of demand. B, determine the elasticity of demand at a price of P equals 10, price of P equals 20, and price of P equals 30. And then graph the function R of Q for the function. That's the revenue function. And find the regions where demand is elastic, inelastic, and unitary. And what do you notice? All right, so let's get to work here. So question A is find elasticity of demand. The function elasticity of demand is P over Q times dQ dP. So this is a function of P. So that means I can have P's in my answer. But it also means I can't have Q's. So what is my Q function here? Well, Q is 200 minus 5P. And that was from right here at the top. Times the derivative of this function. Well, the derivative of that function with respect to P is just negative 5. And so this is going to be two negatives multiplied together gives me a positive. 5 times P is 5P. over 200 minus 5p. And then I can factor out a 5 from the bottom. That leaves me with 40 minus p. And then the 5's cancel. And that leaves me with E of p is equal to p over 40 minus p. And that's your elasticity of demand function. Now let's go ahead and plug in 10, 20, and 30 for each of these, and we'll do the interpretation at the end. So E of 10 would be 10 over 40 minus 10, which is 0.33. It's a third, basically. And then E of 20 is 20 over 40 minus 20. That's actually equal to 1. And E of 30 is 30 over 40 minus 30, and that's 3. And now what is the interpretation of each of these? Well, when the elasticity of demand is less than 1, as it is in the case of a price of $10, we call this inelastic demand. And that means that demand is not sensitive to price changes. And basically what it means is that when there is a 1% increase in price, there is only a 0.33% decrease in demand. So the percent decrease in demand doesn't quite correspond to the magnitude of the price increase of 1%. There's very little demand decrease. So that means the demand is not overly sensitive to the price change at that point. Our middle level here is when E of P is equal to 1. That means that demand is of unit elasticity, or also known as unitary. And that means that for a 1% increase in price, there was a 1% decrease in demand. So sort of the same percentage resulting from both price and demand changes. Lastly, we have elasticity is greater than 1, and that is elastic demand. And that means that demand is sensitive to price change. In this case, we had a 1% increase in price that resulted in a 3% decrease in demand. So that is dramatic based on the percentages there. It's 3 times as much. And those are the 3 scenarios. That covers all 3 parts here. Let's go ahead and graph the revenue function. Now, the revenue function is a little bit different in this case because we're going to base it off of price. So what would our revenue function be if it were based off price? Well, it would be the price of the items times the number of units sold at that price, which is Q of P or the D of P, however you want to think about it. So it's going to be P times, and our Q function was 200 minus 5P. So that's 200P minus 5P squared. That's a parabola that looks like this. Like so. And we have a maximum right here. That maximum is going to occur at 20. This is 40. And of course, this is 0. And if we compare these positions with our example numbers here, we had an example at 10, and that was elastic demand. And so what we notice here is that the revenue is rising at that point. So in other words, you can increase the price by 1%, and you see demand not go down by 1%. It only went down by a little bit. And so that's forcing revenue to increase. On the other hand, we had a position of 30. Right, here's 30. Here's, I should mark this as 10. All right, so my 30 was right here. And if I look at the tangent line there, then we have a decreasing revenue caused by elastic demand. When I increased the price by 1% there, it caused a decrease in demand by 3%. So our revenues was definitely going down. And finally, in the middle one, at 20, that was when we had unitary elasticity, or unit elasticity of demand. That represented the maximum revenue. And so when you get to unitary elasticity, then your revenue is at its maximum. And so the question might be, what do you notice? What are the regions? Well, the regions are this. Over here we have inelastic demand before the maximum. Then we have elastic demand after the maximum. And then at the maximum, we have unitary demand. All right, thanks for watching.